So today's class we'll get to double pendulum. So this is a two-link pendulum, and we'll derive the equations of motion using the Euler-Lagrange method. Then we'll simulate the system, and then we'll animate it. Okay, so the equations which come out from Euler-Lagrange tend to be fairly long, that it's just not it's somehow hard to write them by hand. So we'll have to resort to using symbolic package in Python. So I'm going to start off with the system, draw the system, and then follow the recipe which I outlined to derive the equations. Okay, so length, each pendulum is of length L. We don't really need to draw the second link because it only matters for animation, not for the derivation. However, we need the center of mass of the first and second link. That's shown there, C1, C2. The mass is m1 for the first link, m2 for the second link. There's inertia I1, I2, and these inertias are about the z-axis. So z-axis points out of the plane. So let me draw the axis first. So we have x, and then y. And then if you use right-hand rule, so if you curl your fingers from x to y, your right hand, then your thumb gives the direction for z. So that I1 and I2 is about the z-axis. So just like mass is something which resists motion in the linear direction, inertia is something which resists rotational motion. So here, since the inertia is about the z-axis, it prevents or resists rotation about the z-axis or rotation about the z-axis. Okay, so now that we have this, let's draw the coordinate axis. Since there are two links, I would stick with two frames, and then I need to draw the ground frame. So let's this be the ground frame, always x0, y0. First frame, we will draw x-axis along the link 1, y-axis at right angles, and then we'll choose this to be x2 and this one to be y2. And then this point here is going to be O and O1 because the origin for frame 0 is the same as the origin for frame 1. And then this point, we'll call that O2. Okay, I think that's pretty much what is needed. Now we can start to follow the four steps. First is to get the position velocity of the center of mass, right? Then to write the Lagrangian, which is kinetic energy and potential energy. Third step is to use the Lagrangian to derive the equations, which we'll see it just becomes hard to do by hand. So we'll use Python symbolic package. And then the last step is to do animation. In this case, I'll assume that there's gravity, which is the driving force for the system. So gravity always points along the negative y-axis as shown. Okay, so step 1, position / velocity of the center of mass. Okay, there are two masses here, m1 and m2, so I need the position velocity of both of them. So let's call this point, let's call that point G1 and this point as G2, that is this one. So what I'm interested here is the position in world frame, right? And then I know that from our transformation homogeneous matrices, this is H10 G11. Okay, so H10 is R10. There's a 0, which is a 2 cross 2 matrix, remember? And then this is O101, the placeholder. And the G1 would have the coordinates of G1 in frame 1. I'll use a small g to indicate it's the xy coordinate, and then this 1 is a placeholder. So let's write what R1 is. It's basically the angle made by x1 with the x0 axis. Okay. Now, when I find the angle, I always go counterclockwise. So to compute the angle, I would need to go from x. So you can see x1 points this way to the right, and x1 points down. So to go counterclockwise from x0 to x1, I need to go this way. This is the angle. So I can draw that here just to make it easy to visualize. X0 is here, x1 is there, and then I need to go 90 degrees, 90 degrees, 90 degrees, and then this angle is theta 1. So it's 270 plus theta 1, right? So that would feature in my R10. It's going to be cosine of 270 plus theta 1 minus sine 270 plus theta 1. Okay. Then sine 270 plus theta 1 cosine 270 plus theta 1. These zeros are placeholders. Then I have to compute the position of O1 in frame 0. But the position of O1 in frame 0 is the same as position of OO in frame 0. And that is my origin because it's the place where x0, y0 meet. So this will be 0, 0. And this 1 is a placeholder. Next, I need to compute the position of G1 in frame x1, y1. So x1 is here, y1 is here. What's the position of G1 in that frame? Well, the point G1 is this point. It's along the x1 axis. So its position in that frame is going to be just C1 along the x-axis and 0 along the y1 axis. So C1 along the x-axis, 0 along the y-axis, along the y1 axis, and then this 1 is a placeholder. Along x1, along y1. Okay, so this is an exercise in matrix algebra. If you do this calculation, what comes out is C1 sine theta 1 minus C1 cosine theta 1 and 1, which you can probably see from the figure just by trig, right? So the distance along the x-axis, this distance, is going to be C1 position of this sine theta 1, which makes sense. And then for the y position, it's going to be this position. It's going to be just C1 cosine, but then it's along the negative y, so it's negative. Okay, so you can skip if you don't want to do this homogeneous. It's okay. You don't have to do it. It's kind of obvious. Okay, so this is, if you like, it's the position of G1 in frame 0, and this one is a position of y G1 in frame 0. Okay, so that's one piece. Now we need to get the same thing for G2. Okay, so let's compute the position of G2. So G2 in frame 0 is H20 G22, same formula as before. H20 can be broken down into H10, H21, G22. Okay, so H10 is something we've already computed. So we have already computed this. This was done for the previous position C1 or G1. Okay, H21 is R21 0, O21 1, and we can actually do this. So let's do this. It's going to be R21 is going to be the angle made by link 1 with link 2. So this is link 2 and that's link 1. So the angle is, so if you the same idea, right? So we have y2 x2 sorry x1. So you can see x1 here. It just is this angle. This is the axis x1. I just extended it, and this is x2. So x2 is here, x1 is here. I always go from x1 to x2 in the counterclockwise direction. In order to do that, I need to sweep through θ2, right? The angle between x1, x2 counterclockwise is actually θ2. So that was super easy. It was not as complicated as this one. So we have cosine θ2 minus sine θ2 sine θ2 cosine θ2 0 0. Okay, and then O2 in frame 1. This is O2, but I need it in frame 1, this frame. So the question is, what's the distance of this point along x1? Okay, and you can see that the distance is simply L along x1, and there's no y distance, or y distance is 0. So we have L, 0, and 1. Along x1, along y1. Okay, so far we've got this quantity. It's over here. We have H21, which is right here. We only need to get G22. So G22 is the position of point 2 or center of mass 2 in frame 2, and then this 1 is a placeholder. So if you go back to this figure and you try to see what's this distance along x2, x2 is over here. You can see that it is basically just C2 along x2, and then the distance along the y2 axis is 0. So we have C2, 0, and 1. This is the distance along x2. That's the distance along y2, and this 1 is just a placeholder. Okay, so what we can now do is plug in the value of G2 in here, and then we'll be able to compute G20. So I did that for you. So after doing all the math, comes out to be L sine θ1 plus C2 sine θ1 plus θ2 minus L cosine θ1 minus C2 cosine θ1 plus θ2. And then this 1. Okay, so what's here is going to be the position of G2, x position of G2 in frame 0. And what we have here is going to be the y position of G2 in frame 0. Okay, we need that little bit later. Okay, so that's just the position. We still have to compute the velocity. So we need that velocity because it goes in the kinetic energy for the Lagrangian. Now, we do have, in fact, computed the velocity in the past. So one way of solving for the velocity is to use the Jacobian. So if you go back to, I think it was lecture 8, same figure, same angles, same axis. I'd asked for how to compute velocity of g1 and g2. So we wrote down a formula. Velocity of g1 is jg1 q dot. Velocity of g2 is jg2 q dot. And then essentially, once you know the position of the point g1 and g2, which we've already computed, you can compute the Jacobian and then solve for here is the velocity of g2. So velocity of g2 was from the Jacobian, and velocity of g1 here was from the Jacobian. Okay, that's one way of doing it. So you can use the Jacobian to do it. There's another way to do it, which may sometimes be simpler than this one. So I'll show you this other way. So compute VG10, VG20. So method 1, use Jacobian. VG10 is JG1 Q dot. VG20 is JG2 Q dot. So C lecture 8, I think it is B or something like that. Okay, so that's one way. Here's another way to do it. And you can choose whichever you want. We know the position of G1, right? This is the position of G1, G10. There's an X position and there's a Y position. So the velocity of G1 is simply going to be the derivative of XG and YG. Simple as that. You don't need to do the Jacobian. So we use the second way. So here's method 2. You can write velocity of G1 in frame 0 is you take the derivative with respect to time of G1 with respect to 0. And to compute velocity of G2, you just do derivative of G2 with respect to 0. Okay, so G10 was, we just write it as G10, just to distinguish it from capital G. The caps means that it has that 1 in it. So G10 is C1 sine theta 1 minus C1 cosine theta 1. So d dt of G10 is going to be equal to d dt of C1 sine theta 1 minus C1 cosine theta 1. Okay, so let's do that. I'm just going to write shorthand notation. This is G1 dot 0 equals. So when you're taking the derivative of a vector, you need to take each component and take its derivative. So C1 sine theta 1, take its derivative. C1, the derivative of sine theta 1 is cosine theta 1. And then there is chain rule because theta is a function of time. I need to take the derivative of theta. So theta 1 with respect to time is going to be theta 1 dot. And then same thing for the second term. So C1, the derivative of cosine is negative sine. And the derivative of theta 1 is theta 1 dot. So this comes out to be C1 cosine theta 1 dot, C1 sine theta 1 dot. Okay, so let's write this slightly faster for G2. So G2 dot is going to be d dt of G2 0, which in this case would be d dt. And then I wrote down a formula for G2 from the previous page. I can just copy that. So this is G2. So I just need to write the x and the y component. So the x component is L sine theta 1 plus C2 sine theta 1 plus theta 2 minus L cosine theta 1 minus C2 cosine theta 1 plus theta 2. Okay, so let's take the derivative again. Take the derivative individually. First row, first column, second row, first column. And then remember the chain rule, theta 1 derivative is theta 1 dot. So if you do that, what you get is this C2 cosine theta 1. I just move things around a little bit. Can I also simplify it? That will have all clubbing all the terms in theta 1 dot, and then C2 cosine. And similarly, the second term C2 sine theta 1 plus theta 2 slightly. Theta 2 dot, and then C2 yeah, so you see it's getting cumbersome. So it's just better off writing it by using the symbolic toolbox. Okay, so that's that. This will have two terms. The first one, okay, so this is VG2X, VG in frame 0, and then VG2Y in frame 0. And similarly, the first one was in fact VG1, VG1 X0, VG1 Y0. Right, so this is VG1X, VG1Y. Yeah, I'm just writing it that way so that explicitly so that we can write that later on. So this is step 2. This is the hardest step here is to actually do this calculation. Super easy if you write code. Takes a while if you do it by hand. And that's really appreciate the code once you see how cumbersome these calculations are. Okay, now we need to go to the second step, which is to find the Lagrangian. So step 2, compute L equals T minus V. T is half mVg1 square plus half mVg2 square is of course in frame 0. We write like this. Vg1 in frame 0 square plus half m2 Vg2 in frame 0 square plus half I1. Okay, now I have I1 omega 1 square, but omega 1 square is simply theta 1 dot square plus half I2 theta 2 dot square. Okay, so what's Vg1? It's going to be Vg1 x square plus Vg1 y square. And what's VG1? It's going to be this term, C1 cosine theta 1 for VG1x and C1 sine theta 1. Square plus C1 sine theta 1. Okay, that's not too bad. Now this will become fairly complicated. So we now compute VG2, which is VG2 x square plus VG2 y square. And now if you go and look at this, it starts getting unwieldy. Look at this. This is VG1, VG2x and VG2y. So huge, lots of expression, and then you need to take the square of them and then sum it up. So this is, let's call that A, let's call that B. So A square plus B square. You just don't even try to write it down because it's fairly long. So that's what you'll have. So clearly this expression will look pretty big, right? Because of the way it is. Next, we need to write V. V is M1G YG10 plus M2G should be, this G is different from the center of mass. This G is gravity. And then YG2 in frame 0. Now that's not too bad. What's YG1? Let's write it down. YG1, if you go back to positions, we had positions of G1, which was first page. So position of G1 is C1 sine theta 1. Sorry, my bad. That's position in the x direction. We need the position in the y direction. C1 negative C1 cosine theta 1. M2G. And then for YG2, it's going to be this thing. This is YG2. So minus L cosine theta 1 minus C2 Okay, and the third step is to use this equation. TL Okay, in this case, Qj will be what? It will be theta 1 and theta 2. And then Qj is just 0. There's no external force on the system. So now you can imagine doing this calculation by hand. You need to compute, first you need to get L. Okay, what's L? L is T minus V. What's T? T is this whole thing. Inside is this big mess, A and B. A itself is over here. It's pretty long. B is here. You need to take that, put in here, square it. And then if that's not difficult enough, you need to then take the derivative with respect to Q dot. And then you need to do the same thing with Q. And then once you're done with Q dot, the derivative, you need to take the complete derivative. So you can see that just becomes big. It might simplify something simple, but it's just way too much work. And this is where we don't want to use by hand calculation expression.
And at the end of the second limb?
Position of both. You need a position of both. You mean which one? The number step 3?
What exactly are we solving?
We are trying to get the equations of motion. To get the equations of motion, we need to solve for 3, the equation 3 there. Equation 3 involves Lagrangian, which involves the position and velocity, but somehow the velocity appears in L, which is this one. And then that just causes just a blow up of terms. So we're in a territory where we should not try to do this by hand. So what I did was, in fact, this whole thing, all the things, steps in Euler-Lagrange can be done by symbolic calculations. You don't really need to write any equations. I went through the pain of writing this down, but you don't have to. So the code will do it for you. So here is, and we'll have to go back to this to move further, but let's look at the code. So this is going to derive the equations, and I have written down steps 1 through 3. So I have to define symbolic variables, theta 1, theta 2, omega 1, c1, so on and so forth. I have to define a symbolic pi. Okay, that's done here. So symbolic toolbox has a pi by itself. Pi, like MATLAB, you can't just say pi and it'll give you 3.14. I need a symbolic one. So then I compute, this is just computing H01. You can check from the notes, the same thing. H12, H02, G1, G2. So position is found. Everything is done symbolically. XG1, YG1, XG2 is available. To get the velocity, what I did was, in this case, I used the Jacobian. I said there are two methods. One is using Jacobian, one is take the derivative. I use the Jacobian here. So give me the velocity in the X for G1, velocity in the Y for G1, for same for G2. And then I get the velocity G1, velocity of G2. So this is giving the velocities of vectors, so you'll have an X and Y component. Now the Lagrangian is just half mv square for mass 1, half mv square for mass 2 or link 2, half I omega square for link 1, link 2, potential energy m1 g, the y coordinate. So remember that indices in Python are 0 and 1. So 0th index is x, 1th index is y, and that's why I have g1 1, g2 1. L is t minus v. Okay, if you're curious, we can see what L looks like. Right, we really never simplified for L, but this is what L will look like. I wrote that test so that the code will quit there. But okay, so it's not too bad. That's what L is. Okay, let's move on. So it gave me L. Now we can, I wrote down some expressions last time. I said I can automate this. So as long as you give it what q double dot is, and then I also have to give you q, and let's see. So I define q dot. So q is just you pack all the degrees of freedom in q, that is theta 1, theta 2. Same for q dot. And then you define q double dot, which is the second derivative. Then this code will do create computing the Euler-Lagrange equations. Because Euler-Lagrange equations have this partial derivatives and then complete derivative, you need to use the chain rule, and that's a bit complicated. It just becomes too lengthy if you try to write it by hand, term by term. So this code actually automates that process. I showed it last time. So this will basically give you the two equations, right? You'll have two equations because there are 2 degrees of freedom, one for the acceleration of the link 1, one for link 2. Okay, now we can actually so this goes a step further, but let's just stop here and let's say print UM. Then I'll just make it break or quit. Let's do clear here. Okay, so this is how the equations will look if you do dl dt. So here, okay, it starts here. I guess I cleared. It's going to be a matrix. There'll be 2 equations. There'll be 2 cross 1 matrix. The first row will give you the first row will give you the first equation. The second row will give you the second equation. Did I get everything? I think so. Let's see. Okay, I think it. Yeah, I think it's up to here. Is that right? Yeah, I think this is it. Okay, so could you possibly write this? Well, probably not. It's a mess, right? Just two links. That's why they don't teach this to you in high school. Just you can't write it. Okay, so that's equations of motion. Now we still need to pack this up. We still need to solve. We need to solve for the acceleration. Remember, we need formula for acceleration. Let me take a slide. Well, I should write something. There's a way in which you can work with this. Okay, so once we do this, so this is like a sort of a code management thing. So let's say you do, as I showed you in the code, you do this 2 times for 2 equations, right? One for theta1 and theta2. So what you end up is 2 lines of code, or there's an equation 1, and I'll write it using the way Python gives it. Python will give you a matrix. The first EOM, equation of motion, will give you, you'll have all this huge terms with acceleration and so on. It turns out that these equations have a very simple form, even though they look very complicated. They can be written like this: m11 theta1 double dot plus m12 theta2 double dot m21 theta1 double dot plus m22 theta2 double dot equals, there's a C1 and there's a G1, and I'll talk what these are, C2 and G2. So C1, C2 will, if you have heard of Coriolis acceleration, so you'll have Coriolis acceleration. You'll have a term like something like theta1 dot square. You'll have some velocity term, and then the G1 and G2 will be the gravity term. So it'll have a gravity in it. Somehow there'll be gravity showing up. And then these mass matrices M11, M12, M21, M22 are actually uh, uh, only functions of theta1, theta2. They will not have a velocity in them. Okay? So this is all manipulated equations will have this form, this really nice form. So if you can isolate these terms, then you can write M11, M12, M22, sorry, M21, M22, theta1 double dot, theta2 double dot equals, I'm just going to club these together as, well, let's call that C1 plus G1, C2 plus G2, but we'll club them as N1, N2. So theta1 double dot, theta2 double dot equals this matrix inverse N1, N2. So as long as you can find or compute these terms and this term, you can compute this part. And once you compute this part, once you have the acceleration, you can just do integration, right? So there's a way to do this, which is, if you look at these equations and the form, like this one has gravity. Remember that this is EOM 0, EOM 1. The trick here to get M11, M12 is the following. What you do is you put velocity equal to 0. So this term will go to 0 in EOM1. You put gravity equal to 0, so this term will go 0. And then you put theta1 dot equals 1 and theta2 double dot equals 0. When you do that, whatever remains in EOM1 is M11. You can do the same thing for M12. You can put theta1 is 0, theta2 is 1, and you get that term. Once you found those terms, you can subtract out the right term, these two terms, to get C1 and G1. So That's what you'll see in the code. I keep subtracting things out, and that's how I'll get M11, M12, M21, M22. The code will probably list it this better. Now, once you get M1, M2, you could do this inversion. This mass matrix doesn't look too bad, but when you take the inverse, that thing blows up. So if you try to solve for these things symbolically, like take the inverse symbolically, that whole thing is a symbolic term, N1 into symbolic, then that term is actually will run into maybe a page or so. But if you keep it as a symbolic value and numerically take the inverse, that is, you populate the values of the terms in the mass matrix, and you get a number, a 2 cross 2 number, it's much easier to compute the inverse. So let me show that to you. I don't need this. So to get the mass matrix, there's a trick which is just take the Jacobian. Okay, so it'll give you, then compute the N1, N2. I just put alpha 1, alpha 2, 0. So the left side, which is here. So if I put theta 1, theta 2, both 0, then I'll immediately get N1, N2. That's the trick behind getting N1, N2. Then if you want to find G1 and G2, you put velocity 0, because remember that gravity terms don't have velocity, so they get G1, G2, and then C1 is just N1 minus G1. So this basically gives you M1, M12, M21, M22, C1, C2, which, by the way, I'll take and copy paste in the second part of my code, which basically does the animation. Now, there's another way to do this, which is I told the inefficient way. If you do it this way, which is you take the inverse of M and you keep N as a beam, the right-hand side, and you do this calculation, get to that here. If you do this symbolically, then again, it's going to be a mess. And I actually have done that for you, so you can appreciate that that's not a good idea. So here we have, I'm actually doing it symbolically, and this will give me Q double dot. Let me do clear. And then let's run this. And it'll actually take some while to think. Actually, it'll think exactly when it reaches here. So it's thinking that it's computing this inverse, which is not trivial. And then you'll see something just similar to the equations of motion. It's going to be really long. Okay, so here's what comes out. This is the symbolic values. Okay. Delete here. So this is how it looks like, the equations of motion. Pretty long. So we don't really do that, right? We only save the mass matrix, which the M term. So what I did in the code is I just save M1, M12, M21, M22, C1, C2, G1, G2. Then I populate A, which is a numerical value, then B, which is again a numerical value, take the inverse numerically. So it's all a 2 cross 2 matrix, and that's much easier. So the code here is essentially similar to some of the things we've done in the past, which is define parameters, right? Then I've also defined energy. It's a good way. If you have a system which is conservative, if you can check the total energy, it should be constant. That means your equations are right. That's what I do. And then essentially most of it is the same as before, just that those mass matrix were copy pasted from their earlier code. So you need to do that manually. So if you run this, you'll see the double pendulum.